Now, why do I like this question? For two reasons. I said if you were on time. Number one, and I suppose this is why it's in an extension section, right? You really got to think through what all your equations mean, and even what equation should you use. At some points in your working, it's very unclear. So first requires real thought, and you need to practice at that. It's very hard for me to teach it to you. Like, here's a few steps that you do. Like, the point is that there aren't steps for it. You have to think on your own. And secondly, it's just a really cool result. Like, you can work out escape velocity, which I know, like, the point is not that if you want to know escape velocity, this is the process you would go through, okay? If you're a real physicist, you would just look up the number, okay? But the fact that we can get something like this, which is very complicated, right? From very simple maths, right? We're just, 17 years old or something like that. I think that's kind of neat, okay? And the equations that govern it are very simple as well. So let's give this a go. Where does it start? Newton's law of gravitation says an object falling toward a planet has this acceleration. Now, just before I go any further, because I was talking to some Year 10s recently, it's on my mind. Do you remember from variation, right? That because I've got that x to the minus 2, that's really minus k on x squared, right? So because that x is on the denominator, what this is telling us is the force that's acting upon this object, whatever it is, like in its distance from Earth, okay, that force is inversely proportional to the square of the distance where the force is coming from, okay? This is what we were saying before when I was trying to illustrate why we're looking at equations in terms of displacement. It's because that's how forces act in nature, okay? So that's what we're looking at. So for some positive constant k, and x is the distance from the center of the planet, note that, by the way, distance from the center. That'll be important later. Show that if the body starts from rest at a distance d from the center, then its speed at a distance x from the center is such and such. Okay, right. Now in the question, sort of tucked away in all of those sentences, there are some equations of initial conditions that we want to get at, right? So you can see that last sentence says, if the body starts, okay, when you hear the word start, right, you say when t equals 0. That's indicating where you're beginning, right? It starts from rest, so that tells us what equation? Okay, initial velocity is 0, and at a distance d from the center, okay? So that's the x value, right? So don't be confused, there's a lot of letters flying around. D is just a constant, okay? You may even want to write down here, right? Just to remind you, don't substitute things into d, right? It's not a variable, you can't change it. It's just the distance you start from. Okay, now, we've got to get towards this result. So what are we going to do? From this, where are we going to begin? This equation here, you remember, we learnt acceleration on the left-hand side. We can substitute that for a derivative. Namely, d on dx of, do you remember? Half v squared. Okay. Yes, but they'll totally ask you to prove it sometimes. Okay, and that's why I showed you those two different ways of proving it. And in fact, I've got some interesting practice questions here, which we'll get to. And often the first part is prove this is equal to acceleration. Okay. If they don't ask you to prove it, you can just go for it. Now that's minus k x to the minus 2. Okay, so left-hand side's in terms of x, right-hand side's in terms of x. That's great. Let's integrate. So you get your half v squared. What do I get on the right-hand side when I integrate? Minus 2. Yeah, good. It goes up to a minus 1, so it should be over x. So I'm going to leave that minus k out the front. That's dividing by x, right? I've increased the power by 1, which means division. And I have to divide by the new power. Is that okay? Yeah, that's the integral. Don't forget your constant. Okay, so a bit of cancelling here. That's actually k on x. And we're getting towards an equation for speed, right? Speed at a distance x from the center, okay? Now this is velocity, which is like speed and one better. So we'll know speed and we'll know which way it's facing, but later on we can disregard which direction it's going in. So if we want to get v, let's see what we can do here. V squared is equal to, I'm going to double everything. And now I have a constant to get out of the way. So what am I going to use to evaluate my constant? Right. So I've got an x here and a v, and I've got an x and a v here, right? So at this particular time, those are the values I've got, right? So I will say when v equals 0, x equals d. Okay, so straight substitution, I'm going to work out what c is. So 0 here, 2k on d, plus my constant. Okay, so if that's what my constant is, I can bring it back into my equation for v squared. Okay? Now, I can tidy it up a little bit, take out that common factor, throw a 2k out the front. Okay, so I've got v squared there. Now, pause and have a look. I want to get speed, right? And what I've got is velocity squared, okay? So velocity and speed are almost the same. If I square root, yeah, plus or minus, right? I can't just eliminate that. And then this square root here. Okay, am I missing something? Oh no, I just haven't added them together, right? Now, when you combine these two fractions, you get them on the common denominator. That's going to explain what you see under the square root there. But importantly, right? Here, I've got my equation for v, right? But speed disregards direction. Okay? So, I can actually forget about whether it's plus or minus. I can just say the speed is a scalar, right? So it's just going to be a positive quantity. Because, we don't say I'm traveling minus 60 k's an hour if you're asking for speed. You just take the positive part. Okay? So I ditch the minus, and then when you take these fractions together on a common denominator, you should get, what is it? I think it's d minus x on dx. Yeah? Okay. All right, no problems. Now, what's this? This is the equation for speed given certain initial conditions, okay? Namely that you start somewhere off in space, okay, and then you're not moving and you drop it, okay? So those are the conditions we're looking at. Now when you have a look at question 25, okay, it says a projectile is fired vertically upwards with speed v from the surface of the Earth, okay? So think about what that changes about this question, right? In part A for 25, it says assuming the same equation of motion, right? Now, this is an equation of motion, right? It is one of many, okay? But it's not going to be the equation of motion that stays the same. Why not? Why doesn't this hold for the next question when they said assume the same equation of motion? Where did we get this equation from? We got it from this process of integrating. And then, importantly, when we were trying to work out what the constant was, okay, we stuck in these initial conditions. But these initial conditions have nothing to do with question 25, right? They're totally different. Number one, you're not floating off somewhere in space. Number two, you're not at rest initially, right? You're being fired away from the Earth, okay? So therefore, I'm going to get a different set of these, which is going to give me a different value for C, okay? So let's start working on that. I'm going to get rid of this.